Marge, can you make me co-host again, or is that not possible?
Sure. So, okay, sorry. You're co-host now, and where is Pierre?
And Pierre.
Pierre is also co-host. So people are still logging in. Wait a couple of minutes. And we should be live on YouTube. Yeah, we're live on YouTube. So, okay. So
Hi, Marius.
You're co-host now. And Carlo, hi. How are you?
Hey, Giulio.
Hi, Carlo. Hi.
Ciao. Hi, Sougato.
Hi, Carlo. Hi. How are you? How are you?
Okay, I believe we are ready to start. I think we said wait a few minutes. Okay, so it's a great pleasure for QISS to have the third time our format of the virtual seminar. And it's a huge pleasure to welcome Sougato Bose to give this talk now on the tabletop testing of the quantum nature of gravity, assumptions, implications, and practicalities. And just before we start, I would like to point out to everybody that today we try that if you have any questions during the talk, just unmute yourself and ask the question. So there's no necessity for you to write something in the chat, which might be more difficult for Sougato to read while he's giving the talk. Just unmute yourself and speak. And as always, after the talk, there will be some prepared questions, and afterwards we open the floor for general discussions that we hope to be similar stimulating as the last few times. And finally, let me also mention again, as before, we will have most likely the next session of the seminar in 3 weeks, and you will receive an announcement once all the coordination is done. And with that, I hand over to Sougato. Thank you so much for being with us.
Thank you very much. And let me start by thanking Marius, yourself, and your colleagues for not only for inviting me, but also for arranging this in general. So it is very good that we are staying at home, and it's good to have this nice opportunities to hear people. And definitely I'll try to log in next time. So whoever the next speaker is, I'll be interested in hearing that. Okay. So let me start by so this is based on my presentation will be roughly based on 2 papers. So one is a couple of years older, and which many of you have and I have spoken about before, where we proposed this experiment on how you can test the fundamentally quantum nature of gravity in an experiment. And then more recently, we have written a paper on a more clarificatory note on that. So I will also discuss aspects of that. Okay. Right. So I want to move down to the next page. It seems, yeah, okay, yeah. So outline will go as follows. So first I will just have a brief slide to motivate that why we did our stuff. Okay, so that, for example, there is still no solid empirical evidence for quantum form of gravity. Okay. And then, of course, what I mean by quantum, that I should clarify, and actually, rather how we will proceed in the next step is to define what we mean by not being quantum. Okay. Of course, we will use the term not quantum and classical synonymously. Okay, or not classical and quantum synonymously. that is not the most general way of saying things, but at the moment that since we don't know any other non-classical theory, I will use the word quantum for anything which is not classical. Okay. Then I will state one of the main assumptions in this kind of experiment, okay, which is the locality. Okay? Locality is one of the assumptions, and then I will justify, though this is simply a restatement of things we knew before, that but we'll clarify it more from a physicist's point of view. It was known in quantum information that local operations and classical communication cannot entangle, but it is often not clear the relation between that and how physicists think about a field. So essentially we'll just clarify a bit that a bit more concretely, that why a classical field plus a locality assumption means that, however, I mean a classical gravitational field cannot entangle two separated masses, okay, if they're interacting through this classical field. And then, of course, then I will state our proposal, okay, of how one could, entangle in principle on a tabletop by purely Newtonian interaction, okay. That was, in fact, the main achievement a couple of years ago. I mean, we found that this is kind of not something in the clouds, but kind of near future possible. However, I will justify the practical challenges as the talk goes on. And of course, if you manage to entangle, then it follows from this previous thing that since a classical field, along with the locality assumption, cannot entangle, that means if you do find entanglement, then the field is not classical. And as I said, I'm using the word not classical and quantum synonymously. So that means it's quantum. More broadly, we can say it's non-classical. Now, of course, this kind of reveals the hidden quantum nature of the Newtonian interaction. So here we will highlight the role of virtual gravitons in this mechanism. Okay, so they are the quantum entities we detect. Okay. And also emphasize that though our experiment is a non-relativistic experiment, of course, it is perfectly possible to have a consistent, relativistic description. So just because, some people may think that it is not describable in a relativistic language, it's completely consistent with everything we know about relativity. And then, of course, why we are not yet doing it. So I will spend some time telling about that. Okay. Now, I don't come from the quantum gravity community, and a huge majority of researchers in the world believe that gravity is quantum, and I'm not against that at all. I mean, it's an excellent intellectual endeavor. I just want to say that the evidences is still not compelling evidence. Okay, so this is why this kind of experiment will be important. Okay, there's a lot of I would say compelling motivations. Yeah, there are compelling motivations. Of course, unification, then the singularities, but to every kind of compelling motivation, there are some kind of alternatives available. I mean, some of them, in some cases, may be very dull alternatives, non-intellectual alternatives. For example, if we say, for example, in case of black holes, if we say that we don't want an interpretation in terms of microstates, okay, say we say there's nothing beyond Hawking's calculation. Okay, of course that will raise information paradox, but one could say, okay, let's accept non-unitarity. Okay, so there are you can always find something. I mean, to my limits of knowledge. Okay, so I'm very happy to have a discussion post the seminar on this. And also people have some consistent quantum classical hybrid theories. Some people do have that. Again, I'm not an expert. So this kind of means that perhaps one would like like a real experimental evidence rather than compelling motivations. Okay. Now, of course, when I say I want to show that well, design an experiment to show that gravity is quantum, but we have to define what is quantum. Okay. So quantum has been with us for, over a century now, over a century. And indeed, quantum came through energy quantization, okay, through the ultraviolet paradox. And recently, this has been seen by Marcus Aspelmeyer's group and Lucas Novotny's group for things as large as nanocrystals, that energies of those things, they are quantum harmonic oscillators, essentially. They have quantized energy levels, okay? And earliest, some of the earliest proofs of quantum mechanics where you got order of h-bar corrections to various potentials. So these are what we used to regard as quantum mechanics before. And because these were somewhat easier to observe for electromagnetic field, at least these were the easier things to observe. Okay. Post-quantum information revolution, okay, the emphasis is more on the basic, the very basic principle of quantum mechanics, which is the quantum superposition principle. Okay, there are various other aspects which are directly, indirectly following from the superposition principle. Some, I believe, have a little bit of independent, existence. For example, unitary evolution and superposition go hand in hand. But at the same time, we know there could be evolutions which are, stochastic, non-unitary, which lead to the demise of the superposition principle gradually. These are kind of collapse-like models. So kind of for a little bit, the Hilbert space structure does not immediately mean that you have to have a superposition, but nonetheless, I would say superposition principle is the main ingredient in many of these attributes. Okay, what we will use is one of these attributes in this talk, which is this entanglement conveying ability. Okay, so essentially it is something which follows from the superposition principle. Again, as I say loosely, we will call non-classicality quantum. Okay, so of course we know quantum underpinned by superposition principle. Okay, so in experiments with spins and with atoms. Okay, and this is kind of to motivate a reasonable definition of classicality. Okay, so quantum is on the left-hand side, as when it's a superposition of two paths which can give the right outcomes of the detector D1 or D2 clicking. While if it is classical, to get the right probabilities, of course, there are 4 possibilities, not just P1 and P2, there's P3 and P4, so 4 possibilities. So classical theory is like a statistical mixture of alternatives, statistical mixture of probabilities, while quantum is about the coherent interference. Okay, so this is why the best way to define a quantum field, and I'm already, for convenience, I'm already using notation of a gravitational field, but of course what I'm defining is general. What one can tell is a classical field is that it just has to be a C number. Okay, it has to be a number. Okay, at every point in space-time, it has to be a number. Okay, and it can be correlated, okay, with quantum matter. So different forms, different states of quantum matter. These JKETs I've written to indicate quantum matter. Okay, and then these corresponding to each of these JKETs, there could be a field that is permeating, okay, everywhere in space, and that is the symbol J there. Okay, and it can be a tensor field, it can be whatever kind of field. Okay, but it is a collection of numbers, okay? And that can happen with various probabilities Pj. Okay, so the reason I'm giving this definition in this way is that I'm allowing with these PJs the field to be stochastic. Okay, I want to emphasize that fluctuations alone are not quantum. It's the superposition, it's the coherence between the fluctuations which is really quantum. Okay, so it can be a fluctuating field, that those fluctuations can correspond to states of matter, but I will still define it as a classical field as long as with various probabilities you have a number at each point in space. Now, also, just for convenience, okay, I'm saying a priori that we are working on a kind of fixed background. Okay, this background is nearly Minkowski because our experiment will be conducted near to Earth, or any kind of fixed background we'll get. I mean, this is kind of a safe assumption. We are making this assumption because we don't want to. So we have to. Our experiment starts at a certain time, ends at a certain time. We need that. And we need the notion of distance between two apparatus. So those are decided by the background, okay? And we are not going to backgrounds which would be, definitely not backgrounds which could be pathologically complicated, but also not, reasonably, standard backgrounds in which we place two apparatus so that we have a good notion of the separation and good notion of start and end time of the experiment. And on top of that, we are looking at, these small HPU fluctuations. And essentially, we want to ask whether these can exist in superposition. That's exactly what we want to ask, whether these can exist in superposition. Okay. So now, where were we? Yeah, exactly. So, so this is our definition of classicality, as I told in the previous page. Along with that is this definition of locality. Okay, so all physical interactions are local in nature. Okay, so it's the same place. Okay, in which the matter T mu nu will interact with gravity. Okay, so it's always the same value of R. This is what we mean by locality. I should say, by locality, of course, one need not be very strict. Okay, you can smear out a bit. Okay, so as long as the interaction region is much less compared to the separation of our apparatuses. We'll have two apparatuses which we will entangle. Okay,
Professor Bose.
Yeah.
Just a point to clarify, here in the definition of classicality, you envision, yes, this PJ and then the set. You already envision stochastic mixture of matter states.
Yeah.
Okay. So there is no superposition of matter states at this level.
The J's could be some kind of superposition also, yeah.
Okay.
But only thing we are restricting is that even though J's are some kind of J can be in any basis, okay, but still they correspond to some C numbers in whole of space.
I see. A mixture. Okay. I see. Okay. Perfect.
Okay. So then, right. So what we showed in this paper, we gave some argument, though I say repeatedly, this is not really a new argument. This is more in a physicist's language, but this argument was there in quantum information, for example, before, is that if you combine this kind of definition of classicality, okay, so classicality means this kind of C numbers, okay, these could, then these can just become, labels, okay, this J for different values of H mu nu. So that corresponds to classical communication because it's a classical thing. It can only do classical communication, and locality essentially means that your operations are local. Okay, you can only enact on a local matter with the local field at that place. Okay, so essentially this latter postulate, the locality of physical interactions, corresponds to what we call local operations, LO, in quantum information. And furthermore, this other thing, the definition of classicality that we give corresponds to classical communication, and LOCC together cannot entangle two separated systems. Okay. Perhaps a bit more clarification. Okay, again, this is maybe to some this is a bit unnecessary notation, extra notation, but let me clarify what we mean. Okay, so we had these PJs. With these PJs, we have different field configurations, and these field configurations could have been generated from matter through whatever means. Okay, we are not committing to any certain prescription for generating them at the moment. Okay, they could be generated through some kind of mean field, like Newton-Schrodinger kind of expectation values of T mu nu, or they could have been generated through some kind of stochastic thing, like the matter collapsed left, right, and generated such fields. So we are allowing for all forms of methods, which finally give just a C number throughout space-time, but any kind of sourcing is allowed. Okay. Now, consider any given time. Okay. In that time, there will exist a field configuration, classical field configuration, maybe with certain probabilities, that is Pj, okay? And these operators which act on the system A and system B, there are two systems, system A and system B, okay? I've given psi A and phi B. Their initial state is a product state, okay? A non-entangled state. So it's a psi A product psi B, okay? Phi B. And then these kind of operators, A and B, can act on them. Again, I'm not committing to anything of these operators for them to be unitary. They could be anything. They could be, non-unitary. They could be, open system operators. Okay, but they depend on the H's, the H mu nus in that local site. Okay, which in the end can depend on the T mu nus due to psi and phi at an earlier time. Okay, so if you combine all these, then the net kind of processes which can happen, as you see, these A's will act on this psi A and B's will act on this phi B. There's some extra stochasticity I have allowed through this probability of I and probability K. Different operators can act. They will never create an entangled state. So if you start with the product state, you will always remain a product state, okay? Because whatever your initial situation you have, you create a H mu nu. Then, depending on those, you act locally here, act locally there, and there's no chance that you can create entanglement this way. As you can see very clearly, the operators act on these systems. Okay, so this is nothing but the proof of LOCC, which we have in quantum information, is just a recast of this thing, more in a field language. Okay. Now, so if you buy whatever I said, of course we can have some discussion regarding that later on. Okay, then of course, if we ask this question, is gravity a quantum entity, in the sense that we discussed what is a classical entity, as we decide a classical entity cannot entangle. Okay, so then if we can do an experiment, so this is kind of the cartoon of the experiment. I will of course describe this better. So if we do this experiment and you have two masses and you show that you can entangle them by using gravity, okay? And if gravity was a classical field as per the definition in the previous slide, and also following and interactions were local, so both of those things are just the classicality won't do. Classical and local, both are needed. Okay, then they will never create entanglement, of course. Okay. And that means that if you do find entanglement, then it cannot be either classical or local per the previous definitions. Okay, so we keep the locality and then we say that it must be non-classical. Okay. Now let me tell you the schematic of the setup, okay, that we proposed. Okay, so we imagine two matter wave interferometers with the mass placed in superposition of left and right and another mass placed in superposition of left and right, some distance d apart. Okay, and the superposition length is, say, delta x. Okay. I will later I'll show how one may go about doing that. Okay. Now, how will it evolve? Okay, this will evolve in the following way. So if you multiply out, you will see all these four components there: L1, L2, L1R2, R1, L2, and R1R2. Okay, of course, in these four alternatives, the masses are not at equal distances. For example, you can consider, so those phases are given. Okay, so we are assuming now the direct Newtonian interaction between the objects. Okay, this does not mean that we are assuming action at a distance. We are assuming the Newtonian interaction being generated through some kind of mediating field we are not going into the mechanism. Okay, we are just using it for computation. Okay, we know that this is a good this is a correct result to compute with. Okay, the neutron interaction. So we use the neutron interaction and we find out what are the phases. And obviously you see when the R1L2 is something which will have the largest phase. Okay, is the denominator is d minus delta x. That's the smallest denominator. Okay, all the others, maybe if you have large enough superposition, all others could even be negligible. Okay, but in principle you can take them into account. If all the others were negligible, this setup is very similar to what we call a CZ, or a control Z gate in quantum information. Okay, a control Z gate in quantum information is something for which states like 0, 0, 0, 1 and 1, 0 do not have any phase evolution, while a state 1, 1, so one of the 4 possible states of 2 qubits, only one of them has a phase evolution. So here, by placing the masses in 2 positions, okay, each mass in 2 positions, we are kind of using them as an effective qubit. Okay, the left is one state, the right is another state, and only one of the states has a phase evolution, and that kind of thing can be used to entangle. Okay. Essentially, what is the criteria? Okay, the criteria is, so again, you can do the math. Okay, so if you do these phases evolutions, and I have not yet put the dependence on capital G and stuff, but just this delta phi LR and delta phi RL, if their sum is pi, then this state will become non-factorizable. Means that if you take the L1 out, whatever is with the L1, and then if you take the R1 out, whatever is with the R1, these are not the same state. As soon as these are not the same state, the state is not factorizable anymore, which means it's an entangled state. Okay, so we will get a maximally entangled state even when these two sum up to pi. Okay, that they will be completely orthogonal. So this will be like a maximally entangled state of 2 qubits. Okay. And then you can make this approximation. Okay, though in an experiment this approximation is not good. We will take into account that later on. Okay. But if we make this assumption that the superposition sizes are very large, okay, then we can neglect everything but the phase on 2 of them. Okay, so only delta phi RL is important. That means if delta phi RL can be made of the order of pi, okay, which means like order of unity, then we are done. Then we can entangle the masses very effectively. Okay, when it's pi, then it's maximal. So let's see what is needed for that. And I think this was one of the major realizations when I first realized this. Okay, this is a purely numerological realization. Okay, not that much to do with fundamental physics, but it's purely numerological realization. And of course, this came only because I was interacting with some of my experimental colleagues on kind of possibilities of matter superpositions of the things like left plus right. Okay. So the crucial thing there was the mass. They said that it kind of seemed possible to trap, microsphere masses. Okay, of course, experiment to date is still far behind. People have only superposed very, very large macromolecules, which is about 10 to the power 4 atoms. Okay, that's the world record from Marcus Arndt's group in Vienna. But there are very serious thoughts of superposing nanocrystals, okay, which have 10 to the power minus 17 kg. And then my colleague Peter Barker at UCL, he was trapping in ion traps, these microspheres. And we saw some protocol we had done for nanocrystal would be modifiable and transposable there. So it seemed like 10 to the power minus 14 kg, micron size spheres could be superposed. Okay. Now, so that already is a huge advantage in this GM1, M2. So the most crucial parameter here is the mass, of course. Better, higher the mass, the better, because it's M square, you see. So if you take this 10 to the power minus 14 kg masses, okay, then despite the fact that G is so small, 10 to the power minus 10, okay, in MKS units, if you take time of 1 second, okay, you see it breaks even. So if you take 100 micron separation, with H cross 10 to the power minus 34, this becomes order of unity. Okay. So essentially, this means that this kind of experiment can be feasible. You can give a kind of a pi phase shift or unit phase shift to two masses separated by 100 microns. Okay. Why did we separate by 100 microns? Of course, we could have come closer. Okay. And that would lead to better entanglement. We could probably do with smaller masses, but 100 micron was actually a safe distance. Okay. Because we do not want any other interaction to work. Okay. And even if you were to eliminate everything else, the Casimir-Polder interaction would be there. So that becomes less than gravity after 200 microns of separation. So you can get that order.
A small comment, just.
Yeah.
You just said this is only a crucial observation for what is going on, but only a purely numerological observation, just something to do with what we can do in the lab. You've been very, very humble here, but I think from a theoretical point of view is more than that, because I don't want to go into it, but it seems to me what you're observing here is that the Planck mass might have a role into observability of quantum gravitational effect, even in the non-relativistic limit. So there is it's not just numbers. I think it's a crucial theoretical observation as well. Yeah,
I agree. So I know. So Carlo, you have also pointed this out to me before. I think almost the first time we met. I think this is a very important point. So I was just telling how I arrived at that, but so I was not thinking so much in terms of Planck mass, obviously at that time. But I fully appreciate the point that if you rewrite this expression in terms of Planck mass, then we are reaching those kinds of scales, and something interesting is happening. Namely, this entanglement is happening at that scale, and then perhaps we can discuss this more during the discussion later. So there is this thing that this phase can even become too fast, as you have pointed out before. So that probably happens when you go beyond the Planck mass, right? Yeah. There's also something other interesting thing I wonder here is that so there's something important to tell here, of course, that actually, okay, so what is very wonderful here, so I did not write these expressions in terms of Planck mass, of course, but what is very wonderful here is that usually people think that to reach Planck mass scales, you have to go to this, CERN to the power, what I don't know, CERN to the power 10 or CERN to the power 20. So huge energies to collide things to create, this kind of microgram, whatever, a particle from the collision. But you really need to do that. You can kind of get Planck mass in a different kind of way. Okay. We also know that if you can probe a very short time and space scales, then you might avoid going to high energies. But of course, here our scale, space and time scales are also not that large. It's a very IR thing. What we have is a very infrared thing. Okay, in a very, very low energy gravity. Yet somehow we can Planck mass seems to be playing a role. Yeah, so I think it is surprising. Yeah, that is surprising. But what I wanted to say here from perhaps my thing would be more directed to experimentalists who think, oh, gravity is weak and you cannot do anything with it. So kind of the Planck's constant is fighting the Newton's constant here. Okay, so the Planck's constant is so small in the denominator that it's for the times we have, it's playing a role. What Carlo would like to emphasize is actually we have achieved masses which are now approaching the Planck scale, and that's why we are seeing this effect. Yeah. Now, right. So then what would happen is how you would actually verify this entanglement is also, we proposed a way, is that actually how you would generate this entanglement will be in a way in which the spatial states are correlated with spin states. Okay, so an up state and a down state are going opposite. Okay, up state and down state are going opposite. And then, then if you complete this full interferometers, I'll tell a little bit more about these interferometers. What will happen finally is that when you bring them together, their spatial parts have come back together. So there's no spatial entanglement anymore, but their spins end up being entangled. Okay. Now, having entangled spins here and here is a very good thing. People have already done things like, Bell inequality verifications with entangled spins. So one can verify this entanglement very easily. Okay. So I will go more to that detail later on, but let me show this thing schematically first, why the spins get entangled. So you start with an object in a central position and with spin up and down. So J is the number of the interferometer, could be the first or the second. You have L up, R down. And then there are masses 1 or 2, and then you have this, L, this, when you recombine, L and R both go back to the central. So if you do the whole maths with that, those things included, that the spin and so essentially you replace your earlier math, okay, only L with L up and only R with R down, essentially. Then if you do the whole math, okay, and finally the L and R are brought back to the C's, conditional on spin, you will see the spins, solely the spins in the objects get entangled. So there's one spin embedded in each object, which is what we are using as the handle to produce the the interference and also recombine. Then in the end, these spins would end up having the entanglement. Okay, and then this is very easy to probe by spin correlation measurements, because it's very easy to measure spin in various bases, and you just measure correlation in two kind of correlated directions, and that's a witness for an entanglement. So if this number is larger than 1, the state is entangled. If number is less than 1, the state is unentangled.
Sorry, if you are entangling spins, do magnetic dipole moments not become involved? Now you've got the electromagnetic interaction adding confusion to this?
No, so that is one of the least of our worries. So there are lots of problems with electromagnetic interaction, but magnetic dipole, so the spin magnetic moment, this is the Bohr magneton, okay, it's the individual spin. And when they are separated by these 200 microns, that's much weaker than gravity. Okay, luckily, though it's electromagnetic, because it's magnetic and it's because coming from the Bohr magneton dipole, it's very weak. Okay, but other forms of electromagnetic do bother us. Okay. So now, so then we can just measure the spins and certify this entanglement. Now, like going back to this logic, so now if we do find the entanglement, then according to this logic that I've clarified more, this LOCC logic, okay, we get the fact that if they're entangled, must have been a quantum mediator, okay, because a classical mediator and any local operations cannot entangle, okay, as I have shown before. So if you do find entanglement by measuring the spins, then you can conclude that gravity must have been not a classical entity as my definition before. It has to be something else. Okay. Now, of course, just to revisit the same problem in various ways, for a long time, people have been doing experiments of measuring relative phase shifts due to inertial effects such as acceleration. Okay, so this has been done since the time of this famous Colella-Overhauser-Werner experiment, bouncing cold neutrons. We have also done some of those things to measure various metric components. The question is then of course those experiments, many of them already exist, like the COW experiment. Then of course one would say that why not just use them? Okay, why do we need to do this complicated thing of going to entangling two apparatus? Okay, the question is that those are still classical gravity can still change those phases. Okay, so if you have a classical gravitational field somewhere else, that will still rotate the change the relative phase of two arms. And it's completely fine to use a classical gravity field to interpret those effects. So they do not uniquely point out the quantum nature. Okay, so they don't point out the hidden quantum nature of the interaction. Okay, just to clarify this, so what is quantum about the Newtonian interaction, you might ask? Okay, Newtonian interaction has been divided, found out in the 1600s. Okay, people have been using Newtonian interaction since 1600s. Okay, but there is also a quantum interpretation of it. Okay, the quantum interpretation of it can be thought of as an exchange of off-shell gravitons. Okay, so you have all kinds of energies of gravitons going in superposition of different energies. And you can do a fully, relativistic calculation with the appropriate relativistic propagator, and also no problem with gauges. You can use gauge-independent parts of propagators, and you do get the Newtonian interaction. Okay, so this is quite a textbook thing in, when you start reading quantum field theory. So there is this kind of quantum communication, this, off-shell propagator going between two entities, and that can generate the Newtonian interaction. Okay, of course. So one might ask that, so why have we not found Newtonian interaction to be quantum so far? Okay, though Newtonian interaction could be fundamentally coming out from a quantum process, just like the Coulomb interaction. Coulomb interaction comes out fundamentally from a quantum process, virtual photons being exchanged. If gravitational interaction comes out fundamentally from a quantum process, what is needed to reveal that? And there, these kind of COW-like experiments do not suffice. Okay, there you have an alternative interpretation where you can use a classical field at that place to change the phase. Yeah, of course, gravity changes phases. Okay, but you can have a local classical field to change the phase. So though Newtonian interaction may fundamentally be quantum, the Newtonian interaction, so you might be having a quantum interaction with the Earth, but that's not being revealed through the kind of experiments we have been doing so far. Okay, so earlier experiments were, of course, not at all in, nothing was in superposition in earlier experiments where you're just measuring force. And then later experiments from the 70s, such as the COW experiment, though they were measuring relative phase between some states of quantum matter, they could still be interpreted without having a quantum mechanism. However, when you take two such things, it's like putting the Earth in a superposition in this COW experiment and having another one, then if you took such a classical field, you will never develop entanglement. So if you do develop entanglement, then you're forced to conclude that this is going on. A virtual graviton exchange is going on. Okay, so and nothing else, nothing less will explain this. So there are various alternative theories. For example, there are these kind of things which measure a position of a mass and then change the mass at a distance according to that position. So there could be such kinds of things. There could be stochastic theories whatsoever to effectively build the Newtonian interaction, but none of them will result in an entanglement. So for an entanglement, you need to have this kind of quantum communication. Classical communication will not suffice. Okay. Now, what is the quantum of a virtual graviton? Okay, why do we call it to be doing quantum communication? Because essentially you have these huge number of intermediate states over all energies, which is superposed in the middle. So you have an initial and final state where there are two masses, okay? And then the intermediate states involve these gravitons, okay? And these energies can be anything, okay? So it's really superposed over many large things, okay? However, that superposition alone is still hidden. When you are measuring just the Newtonian, say, displacement of two things or doing even interference of one with another, it is still kind of hidden. Okay, to reveal it, you really need to go to these two interferometers. Okay, so this is a cartoon picture. Okay, in terms of that. So here there is obviously there are four kinds of superpositions. So there are two kinds of superpositions here. So there is the one where the in each graviton exchange is also a superposition of over all kinds of energies. Okay, off-shell energies, while there's also a superposition of where they're emitted and where they're absorbed. Okay, so this is kind of I would say this is kind of verified in this kind of experiment.
So Sougato, let me just mention, I mean, usually we are aiming for roughly half an hour. I see that you're already kind of getting towards the end.
Okay.
Just to as kind of a heads up.
Right. I think it will be another 5 minutes, maybe. Yeah. So
I think that works.
yeah, maybe 6 minutes. Yeah, let me see. Okay. So now just to say that the thing, there was some opposition from some people that this cannot be recast in fully relativistic QFT language. For example, in quantum field theory, we do not have masses, but we have excitations of fields. Okay, these are huge masses. Okay, as Carlos said, like really approaching Planck mass. But the states we take is that creation of the mass here or creation of the mass there. If we take the masses to be excitation of a field, they are excitations of many fields, all electrons, all protons, everything. Okay, but it's whole mass is here or whole mass is there. Okay, this is what we call a known state. Okay, so all particles here, all particles there. Yeah, n 0 0 n plus 0 n. Okay, so you can explain the matter state definitely in QFT language, and causality is not even an issue because the matter states, okay, will of course not interact when they're outside the light cone. They will influence each other when they're inside the light cone. So it's just that. Okay, so I won't spend too much more time here, but it can all be made consistent. So this experiment is of course non-relativistic domain, but doesn't mean that it's not describable by fully relativistic theory. Okay, the interaction will start of course after the light speed between them. Okay, it's just follows from quantum field theory. Now, how we do this? This is now the how we implement that. Okay, so we use the Stern-Gerlach effect. Okay, so essentially these are ancilla induced superpositions. This is Schrodinger's technique from a long time ago. Okay, so you have one bona fide qubit. Okay, you place in a superposition up and down, and then you use a magnetic field gradient, okay, Stern-Gerlach. So that magnetic field gradient splits things, okay. At certain time, tau by 4, you flip the spins, okay, it starts decelerating, okay. Then they stop, turn back, then you again flip, they start accelerating and they come back, okay. So this is called Stern-Gerlach interferometry, and this is how you split and recombine, okay. Why does it not go up? Yeah. And we did one more change for our current system is that at these kind of shoulders, we change to nuclear spins. This gives us kind of, it becomes independent of this magnetic field gradient and freely falls. And also nuclear spins have a lot of coherence time. So you can let masses fall next to each other for a long time to interact, okay? And what we found is you need this 10 to the power 6 Tesla per meter gradients. This is a practicality, what we need. These exceptionally high gradients, but they are there. I mean, record players have this or higher gradients near them, but you have to be, the magnetic field gradient has to be very near to the mass. Okay, that's the problem. And then you can, in time of a second, okay, so I see I've forgotten to write the time here. So in about a second, you can get these kind of 100 micron separations. What we are doing practicalities, I won't go into too much detail, but these are the two main bullet points for individual superposition, okay? So you need a large splitting. As we said, large splitting requires this large magnetic field gradients as shown here, okay? And the next challenge is the worst of the challenges is maintaining coherence. So once you have created it, I'm recombining, I'm including inside splitting. Splitting and recombining are opposite processes, okay? So if you have a good mechanism to large split, you'll have a mechanism to recombine. But maintaining coherence is definitely going to be the major challenge, okay? In this picture, for example, what have we taken to do the coherence is this helium gas will kind of blow through the diamond to cool it, not just motionally, but also internally, because it should not emit, black body radiation, okay? And then vacuum so that the atoms do not hit it. So this is the major challenge for individual superpositions, and major challenge for two things are that this mass should be large enough, then neutral. Okay, neutralization is very easy to do these days. People just shine UV to the object or to its surroundings, depending on charge. Okay, we will need to do physical rotation about axis. Okay, this is also people are starting to do that. This will cancel all multipoles inside object. There are charged multipoles. and then the separation for Casimir, okay, appropriate separation. So these are the challenges. To make gravity dominant is the second challenge, but that's less of a challenge. The major challenge is maintaining the superposition by far, okay? That's where we'll probably get stuck for a while when we try to do that, okay? So I just, before ending, I point out some other, related works and kind of implications. So the implication of the experiment, of course, can be also be thought of as that it proves that geometries can be superposed. And then there's this paper by Marios and Carlo, very adventurous one, that if one can even take the experiments to a bit later domain, then you can perhaps probe the discreteness of time in the Planck scale. There are other things which there are some paradox resolutions which point towards the quantum nature of gravity, which is an interesting work. And then also there's this thing that in a recent paper I saw by Richard Howell and some of the people in the audience, as about other ways of probing the quantum nature of gravity. Okay, so I won't go into those details because many of the authors are here. I just end up with presenting some of our papers. So I have spoken about these two papers. The latter one is to appear soon. Okay, this kind of giving justification for what we did. And then we have some other things which build towards it. So we were considering this large mass superposition. So that's how to make the thing is in those papers. Okay. Yeah, thank you for your attention. Let me take it. So what was my time now?
A bit more about 45 minutes. I think it.
45. Sorry. Really sorry. Yeah. I'm done.
No worries. So please let us all thank Sougato. So you're very welcome to unmute yourself and clap. And now I believe we have some prepared questions and comments by Andrea. Is that?
Yes. Hello. Hi. Thanks again for the very enlightening talk. And I wanted to ask you mainly two questions. Maybe I'll be fast so that people can talk. Do you need to consider gravitational effects from nearby masses as perturbing they could create noise in the experiment?
Okay, so this is a interesting question. Okay, so one thing is what kind of perturbations we consider. So one of the most important noises which has been there in kind of say in the LIGO setting is called Newtonian noise. Okay, so a movement of nearby masses from their position where they were. Okay, so the experiment will be normalized to static positions of things. Okay, and very rare events, some things would be filtered out. Okay, very regular oscillations would probably also be filtered out. Okay, but these would only affect the detection. Okay, of the like how it would exactly come in, as you said, as a noise. Okay, but it will not come in as it will definitely not create any artificial entanglement. So it doesn't make a false signal. Okay, it will just be making the signal more difficult to observe. Okay, however, if the masses are close enough, okay, and you have some accelerometers nearby, okay, so you use the kind of accelerometers, you kind of use benches which are more vibration proof, and they can sense what is the acceleration to both the things. Okay, so you can then feedback and manage those things. Okay, so if you want to know, so an estimate of, for example, an estimate of what happens to Newtonian noise for kind of one of those kinds of interferometers, we have done some analysis in this paper. Okay, this gravitational wave detection. However, that is in a much more challenging domain. You can use such interferometers to detect gravitational waves only if you you make meter scale things, but of course, much lower masses, nanoscale masses rather than microscale. And in that domain, at least we have seen what can be done. So you can build 2 or 3 interferometers in parallel and compare the signals. Okay. Now, we don't want to go into that, but there is this thing that our interferometers are also kind of the most sensitive accelerometers on their own.
Yeah.
So perhaps one can normalize with respect to one, like keep one in the distance.
Another one. There's another one next to it. I see.
Yeah.
And
So I acknowledge there's a lot to develop here. It's not the end of the, on the practicality side, it's not the end of the story.
For sure.
Far from that, far from that.
And as a second question, I had a curiosity about the experiment. And when you do the experiment with embedded spins, the spins start in an eigenstate, so pointing in the x direction, I think, in the way you presented. And then if they come down entangled, then if I'm not mistaken, they're not in an entangle, they're not in an eigenstate anymore of the spin in that direction. Do you have a physical understanding of how the spin is changing, like what is transferring angular momentum?
Yeah. So the spins are, entangled with the masses, right, in the midway. So an up spin goes to the left and the down spin goes to the right. Okay. So only at that stage, the spin, coherence in the, the spin was pointing in the x direction. That's already washed out when you do the Stern-Gerlach splitting. Okay, right. Because of course, there's a lot of momentum transfer already from the, from the magnetic field gradient. Okay, so you are asking that the spin in the x direction, where is it getting the chance to spend, to change its angular momentum? Okay.
Yes, because if the other mass wasn't there, it would come back into the.
Yeah, so I think it's best there to regard the spin as, say, part of an open system with the mass in the left or right, like its environment. So it's being dephased, dephased and undephased. So the spin information is being washed out, and when it's undephased, it finds it to be entangled with something else.
Okay. Okay, thanks. I would have other questions, but I think I can leave open to the floor.
Okay. Oh, I see Lucien. Wow. Okay.
Hi, yeah. How are you doing?
Long time. How are you?
Yeah, long time. Yeah, you look the same as last time I saw you. So yeah, my question is it's conceivable at least that when the two particles interact, they also get entangled with different quantum states of the gravitational field. And if that happened, then the entangled state that you get would also include different states of the gravitational field, and so it would act as a source of decoherence for the quantum experiment. So presumably you think that won't happen, or what's happening there?
Yeah, so it's a very good question. So there are 2 parts to that answer also. Okay, one of the things is, this is also the reason why I brought in this virtual graviton picture. Okay, because essentially what you have is kind of a coherent interaction between the 2 things. So if you take the 2 mass state, at every point, if it was the ideal interaction, the neutron interaction was going on, even if it's mediated by gravity, the 2 mass reduced density matrix is at every point of time in a state which is arbitrarily close to the pure state. Okay, which means that the mechanism is something where it is not getting entangled with gravity. Okay, and this kind of or getting hardly entangled with gravity. Okay, there could be some degree of entanglement depending on where you say there's some Planck scale, so there could be some.
Why is it always close to the pure state?
So if you just take the evolution, so this is my state, right? The evolution of the 2. So that I can do the calculation directly by this phase. So I can do for example, so I can do the calculation directly computing this phi RL and phi LR from the neutron interaction, and you see there is no entangled gravitational state with that. You see, if it was there, then there would be some reduction in visibility while the entanglement is building up, and then again, it will go away when you recombine. But in this case, there is no lack of visibility if you take the combined density matrix of the two things at any stage, which means the mechanism is this peculiar thing where the system has hardly entangled with the gravitational field, yet this exchange of, so it's at kind of step by step, very low entanglement has gone, something like that. Okay, so this is only permissible through this virtual graviton like thinking. Okay, so that's the first part of the answer. Okay, but there's also a second part of the answer, which is that of course this will involve accelerations and things, so there will be also emissions, of real gravitons. So there will be emissions of on-shell gravitons, so they will decohere. Yeah, but that effect is very small effect.
Small, okay.
Yeah. But if you find this puzzling, it is the only way to get into peace with this is to think in these virtual graviton pictures. But when virtual gravitons are exchanged, they do not in the intermediate case get entangled with the systems, yet they can convey entanglement.
I mean, it does mean that the theory of quantum gravity has to be in terms, it has to have these features, but that seems
it's not just not, so even electromagnetic interaction, you see, the electromagnetic field does not get entangled with the state of the when you place a charge in a superposition of here and there, the two charge state and the two charge state will remain a pure state. So the kind of visibility dip that you are hoping for will happen only through this other effect, emission of radiation, but will not happen through the thing which sources the interaction.
Okay, great. Thank you.
Can I make a comment on this discussion?
Okay.
Because I think if there is a way to reconcile what both of you are saying. So Sougato is making the point that there is no significant entanglement of the radiative degrees of freedom of the gravitational field with the masses. But the way, the way we interpret this phenomenon after Sougato did it, we just rewrote something with putting general relativity in with Carlo, is actually by indeed considering that the state of the gravitational field is entangled with the spin state, in the sense of, in a very simple sense, that you have a different macroscopic metrics. So if you have a mass that is at distance d, or two masses that are distance d, or two masses that are at a distance d prime, is not a diffeomorphically, they are not diffeomorphically equivalent metrics. But you are considering a much simpler degree of freedom, gravitational degree of freedom. It's essentially the scalar degree of freedom of the metric. Is really not the radiative part. So the way we understand is that indeed there is entanglement with the gravitational field, just not with the gravitons.
Can I jump in here?
Yeah.
I think that Marius is right here. There is definitely entangled with the gravitational field during the time t and not after. There is a remaining entanglement with the gravitational field after, due to the radiative modes, which can be computed explicitly. There's calculations in electromagnetism about that, which can be just, it has been done, transported to, and one see that the entanglement after the masses have been recombined, there is a residual entanglement with the gravitational field, and you can compute it, and it's very small, and so you can compute the coherence, and the coherence is completely negligible. And physically, it's just when you move these masses, you excited some gravitational waves, of course, that are going far away in the universe. So from far away, you can measure something to distinguish the two branches. But that's obviously minimal because it's a disturbance of the gravitational field. So that answer nicely, as you were saying, Sougato, Lucian question, yes, this is the coherence, but it's very small. It can be computed explicitly. But in between, I would say that there is entanglement between, if you want to say the virtual graviton, the virtual graviton emitted in the two branches are different. Let me make a more general comment since I'm here. You know, Sougato, I'm extremely excited by this experiment. I think it's this proposal experiment and this idea. I think it's the most interesting thing happening in quantum gravity in the last years. I teach a class in quantum gravity. I start with it, and I teach a class in general relativity, and I close with it to master students. And I think it's enormously interesting, first of all, because if you can do the actual calculation, the actual experiment is fantastic. This is a super result. Even, and I hope that's not going to happen, even if it cannot be done concretely, it's so clear conceptually, and it's such a fantastic ideal experiment to consider, even if it cannot become real, which is of enormous value, I think. And you, I mean, everything you said, of course, is completely right. But you talk to different communities, and you have to adapt your language to different communities. So when you try to talk about quantum gravity, you try to use the language of quantum particles, which is fine, and it has its it makes some people happy. It makes some people something more clear, something less clear. Now, if you think about quantum electromagnetism, there are two formulations, there are many formulations of this, but there are two. One, if you can think in terms of photons, and one you can think of wave functions over classical configuration, the Maxwell potential if you're in one gauge, or some other component of the field if you're another gauge. So you can think of quantum field theory either as a theory of particle or as a theory of field. It's just two different pictures, just two bases in the Hilbert space. It's not anything deep or strange. You can go to the Fock basis, which is particles, or you can go to the field basis. And of course, I mean, you have to be careful if there's matter, there's gauge, and things like that. But those both are clear. Now, if you think in terms, and you do have to think in terms of quantum field theory, exactly for the reason you said, if you want to bring locality and quantum interaction entangled together. If you think in terms of particles, you get this picture about virtual gravitons. If you think in terms of fields, which is what Marius was saying, things are in a sense much more clear. You're splitting a mass, and therefore there will be some transient dynamical phenomena, but who cares? These are so small. I mean, if you want to satisfy people who complain, we can compute those things, but forget the transient, because we know that in the C going to infinity limit, it will be negligible, its effect. But nevertheless, when you split the manifold, you have two little, if you want, Schwarzschild geometries, or in the approximation, two little geometries with two different G00, which are entangled. So this is a direct entanglement between a split particle and the gravitational configuration. Now you have your other particles, so you have your entanglement between the gravitation and the other particle. Then when you bring the two coupled particles together, of course, the gravitational field, as you want, the static part of the gravitational field goes back to just one. So you don't have any more entanglement between gravity and the particles. But if you see the things this way, I mean, here, most of the people listening to this presentation are relativist. So they think gravity, not in terms of gravitons, but in terms of geometries and fields. And I think if you look at all what you said from the perspective, which in this community is more common, course, if you talk to particle physics, nobody understands field language. It becomes much more clear that what you're talking about is a superposition of geometries. And there's no way to make sense of, if you can do the experiment and get to the number, and if you just think about quantum field theory in terms of fields, there's no way to think about the result coming out unless you have a superposition of fields, or macroscopically distant fields, and therefore a superposition of macroscopically distant geometries. That's my view of why it's spectacular what you're doing.
Right. Yeah, I think this can be reconciled. Yeah. Yeah, there are a couple of things here. So exactly. So I think your and Marius's paper is kind of the number basis, phase basis counterpart of what I say.
New, of course. It's just we're telling the story in a different language.
It's a different basis, yeah. And what you're saying, I think that may be a more appropriate answer to Lucien's first part of Lucien's question, the entanglement during the. So what I did say is that that even during the evolution there is no entanglement with the field variable, but on that I had this implicit assumption that you could actually do an experiment on the masses which would take their reduced density matrix independent of that field, which you cannot do. So when you are doing the experiment with those masses, you are doing it together always. So that's why I think that resolves this. So when I saw this notation in your and Mario's paper that LGL plus RGR. So both my colleague Anupam Mazumdar and I, so we did not like so much this. So of course the notation GL and GR automatically kind of LGL plus RGR would signify some kind of entanglement, right? And of course at the end of the experiment they all come back, no problem, okay? And at my thought was that even at intermediate times the GL and GR are so close to each other, which of course is fine in both pictures, that there's hardly any entanglement. Though there's some entanglement, it's not a measurable entanglement, okay? Yeah. But on the other hand, there is also this thing that even if there was a measurable, if you superpose black holes or something, so very geometry, I think the problem is that you probably cannot separately measure the reduced density matrix of those four things alone. So that might resolve also.
Yeah, I agree.
So just while you're discussing this, how does this relate to the problem or the issue of locality, that the interactions are supposed to be sort of local field interactions, and so it seems like there ought to be entanglement from that point of view with this quantum gravitational state. So how does this discussion relate to that issue?
Exactly. So Lucien, the question you ask is exactly a question which was asked to me the very first time I presented it somewhere, was by Kaslov. Okay, so naturally we think of entanglement as being transferred from place where a little bit of entangle has to entangle a bit and go there and transfer the entanglement. Right now, here at every point there's hardly any entanglement.
Exactly.
Okay? So this with this virtual thing, but it must be very small steps. Okay, I would hazard. So say if you are doing this in a crystal lattice, for example, to see the amount of entanglement, how small they are, you would have to go to the lattice scale. Then you get some units of entanglement per interaction or something. So I guess at the level that you cut this off at some Planck scale or something, there would be that would be the tiny bits going each time, I guess. But at the very low energy, long distance scales we are talking, it's kind of negligible yet accumulative. I mean, it kind of sums up. The integration gives the entanglement, but somehow
sounds like a quantum Zeno effect almost.
Yeah, I mean, I think this is good to explore. I mean, I've thought often to explore this, but never really sat down with this. But I think because we went then to this particle picture. So my collaborator Anupam is more from a quantum field theory background. So there, since the virtual graviton picture kind of solves this issue already, okay. we did not pursue it further. So I guess there would some entanglement may come back if we put a high cutoff in the virtual graviton in that picture, or yeah. So I have to think a bit more about that how the entanglement is transferred. The best answer I can give you now is through infinitesimal, steps, so that in no point at every point there's hardly any entanglement. And there is the entanglement which Carlo and Marios is talking about, that left, but that entanglement is not observable independent of the mass, perhaps.
Well, the only way to measure that is, to put a clock on the second particle and wait the clock to go in a superposition. But of course, the effect is small. So you wouldn't measure it unless you wait the full time and right. You get to the end. And that's, it seems to me that's the physics of what you're saying. It's not that during, in between, you can easily measure that.
Yeah,
so conceptually it's there, but so conceptually, when you split one of the two masses, suppose you move half of it apart. In that branch, there are some fast radiative effect, that very rapidly bring the metric in that branch to a slightly different Schwarzschild metric. So in each point, the potential is a little bit different. All right, but in which sense is measurable? Well, one sense it is measurable is just to do what you're doing, which is measure the dephasing of a clock with respect to the other one, or the dephasing of a clock of sitting there in two different in the two different branches. But before you can actually pile up something measurable, you have to go through exactly the long time you need to build these things. At the end of which, if in your experiment you bring together the source masses, you're just not having a superposition of geometries anymore. So physically, I understand exactly what you mean when you say, well, but I can't measure the entanglement with gravity unless I'm doing what I'm doing. And so at the end, the only residual measurable entangle with gravity is whatever was dynamical to start with, which we know is very small.
I mean, this is also kind of, so let me add, this is also kind of related to the origin of this kind of proposal, is that, if you want to find out the entanglement of LGL, that entanglement LGL plus RGR, the best way is to take that to another mass and measure it, rather than somehow, and that takes place in an infinite number of small steps, but in a finite time. Unless you're going to radiative degrees of freedom, which Carlos. So if you do something very fast, you will get something on shell independent out there, which you can try to measure.
I have a question.
You will never, because that's just like measuring gravitational waves. So
yeah, exactly. So you can probably try to do a very, but it's very hard. In our thing, you wouldn't be able to. Hello.
I have a question. Sorry. So like this experiment, like shows that, like if realized, like if the results, like if it's possible and it's realizable and the results are good, it shows that the gravitational field is not classical. But my question is like, with the linearized picture of gravity, you can explain the effect, but this is maybe for some people going like too far. So my question is like, what is the minimum requirement of non-classicality of the field, of the gravity field? Like we know, like I'm from more information theory background, that we need like two non-commuting observables, basically like to generate this entanglement, like this to mediate entanglement. So which features of the field will be basically these non-commuting features?
Yeah, so what is the minimal thing needed? You're telling, so that is in other words, can we broaden the definition of so I have taken not classical synonymous with quantum. Okay, but of course, as you know, that is there are lots of quantum things I told there, and something which shows any one of lots of non-classical things are there, and if something shows only one of them, does not mean that of course I agree with you, does not mean that it's fully quantum. Okay, so all those quantum things that I mentioned there, they are very closely interrelated. That's the problem. It's very difficult to separate them apart. But there possible are wiggle windows that when one thing happens, the other doesn't happen. Okay, so I have always gone through the side of that you need at least you need the superposition principle. Okay, so which in our basis, the particle basis, which I showed a picture of the superposition. In Carlo and Mario's basis, it is the field basis is a superposition of geometries. Okay, so the non-complementary basis that you heard was there in the paper by Vlatko and Chiara. They proved that you need that. Okay, so again, it's very difficult to say what is minimal. Okay, can you do with something less than a superposition or less than complementary base is difficult to say. So I would say that I mean, definitely superposition suffices. That's the thing. Okay. What is necessary is difficult. But you see, it's not just we are not just trying to reproduce the entangling thing of our experiment. We are trying to reproduce all features we know about Newtonian interaction. So we know it's a continuous interaction, it's a continuous accumulation of phases. So we know a lot of other things from the past. So this is why we come to narrow down to more specifics. If it's an abstract, completely unknown field, then these questions arise. But since we know so much about Newtonian, it's far more constrained than just being, complementary basis or just being superposition. So this is why these virtual gravitons had to be the specific kind of superposition. Okay, so we have to, so we are constrained by that also. We are constrained also by the 1/r and the so we are not we are a bit further constrained than just any quantum thing in the middle. But sorry, I said any quantum. So your main question, I think I have not answered, because non-classically, where do you need to stop in the could there be some other classical aspect of this gravitational field which is not on, and yet this I think it's a very good question. Yet this effect is being demonstrated. Okay, but I would say it's not just this effect, but also the 1/r and the Newtonian thing which has to come.
So, and a second question that, I'm sorry, it's so. Because I came really from an information perspective. So for me, I need more or less, if you have a hint or something about which will be the non-commuting observables or operators for the gravitational field, basically.
Right. So of course those the number. So those bases already came up. For example, yeah. So the number basis and the field basis, right? Okay. So so there are it's like so you think of any electromagnetic field, for example. Okay. Then we take so it's like, very roughly speaking, the electric field and the magnetic field are not commuting. Okay, so so it's like this. So one behaves like the position, one behaves like the momentum.
Yeah.
And there will be similar.
If I may, is your first question well defined?
What do you mean?
I mean, given any experiment by itself, it doesn't prove anything, right? It just says that in that particular, in London at some point, something happened. I can come up with a theory that says everywhere the opposite happened, but in London that day, something special happened. I mean, it doesn't prove out that theory. So your question, I don't think one can ask, one can consider a number of possibilities or theoretical frameworks or theories and say, oh, look, this experiment contradicts this prediction.
Okay,
So,
yes.
so
Well,
only make, and in quantum gravity, there are not this list of things. There are very few. In fact, one which people have discussed is that gravity is not quantum in the sense that is classical, or that you can have a statistical superposition of geometries that you interpret statistically in this knowledge, and it interact with a quantum system. And there are various ways of doing that. So one can ask if specifically those, this experiment successful rule this out, and some of the papers around claim is explicitly so. But otherwise, I think it's extremely vague, seems to me. And unless you have a specific something in mind, I could describe quantum gravity with this particular framework, which is not quantum mechanics or classical mechanics. Would this specifically framework be ruled out? Maybe that's what you have in mind.
Yeah, I agree with your point. Maybe like the question I had more in mind would be what features quantum theory of gravity should have in order to not be falsified by this experiment.
Yeah,
would be maybe more in those lines. I don't know.
Yeah, so this is why I took all that effort to define what I mean by classical. Yeah? And what Carlo is telling, that you always work within a definition of things. There is this paper by a group from Queensland, I think, that they take a hugely expanded definition of what is classical.
Mm-hmm.
So if you define classical in a very expanded way, then maybe there is some chance of again, it comes to the philosophical point. I mean, I wouldn't go to define that as classical, So that's I mean, classical quantum again is a name of a terminology. So there is okay. It is within these limited definitions. This cannot be explained.
That's fine. Thanks.
I have a comment on this point because I don't remember the paper, but so one thing is to say what features do you need to have in order to create entanglement, and whether you can have these features in something that you don't necessarily call quantum. The other thing is to get the production of entanglement exactly at the physical regime that you are predicting in your paper, where you have some specific experimental parameters, a mass, and a time duration and a distance. You're not saying I'm going to get entanglement whatever I do. I'm going to get entanglement if I put these parameters to be exactly these values. And this has to do with the fact that you have Newton's theory and you have a theory like a linearized quantum gravity that has this theory as a limit. So one thing I noticed is people coming up with papers saying, in principle, I might get entanglement creation, but there is no proof that you have the Newton's theory as a limit, right? So it's not actually a prediction in reality.
Yeah. Okay. Yeah. So I think so. So I would like to. I agree with that. So anything that people do also has to have this constraint. The Newton's theory should at least be as a limit.
Yes, and I think they should get it. It seems to me sometimes they leave it as an exercise to the reader, but it's like, I mean, first get Newton's theory and then we discuss about it. Sorry, just a comment.
I have a very simple question, which just has to do with analogous claims about the electromagnetic field. So none of us has any doubts that the electromagnetic field is quantized, but if I ignored all the evidence for that, and I just tried to run the analog of your experiment in that case, I'm curious, first of all, I imagine all the steps go through, but you've probably thought about it and I have not. And then the second question would be, is there an experiment that does it that way?
Okay, so this is a question which has always been asked to me in almost every talk I gave on this thing. So I remember Carlo has also asked this question to me, and I think many people. So almost this is the first question people come up with. Yeah, and of course the answer is that it can be done. Okay, so Anupam and I were discussing with an experimentalist, but the thing is that in quantum computation, people have already done it in some sense. Okay, so when we entangle trapped ions, yeah, we entangle them by their charges. And so actually Christoph Wunderlich was the inventor of that mechanism where you do really quantum gates by spin magnetic field gradients, split the ions, and the ions entangle. So I mean, this I knew and was in my back of my head. So probably my idea came from that, okay, in something. So only they do it in such a small separation limit that you hardly have a superposition because the field is so strong, even tiny things can, you know. So it is completely analogous. I mean, there's, we, of course, we do not need to go through that route because we have, you know, even better proofs and stuff. But in case of, what I can probably say is that strangely, in case of gravity, the thing has been reversed. All the things that were so easy for electromagnetism, okay, so finding, you know, these corrections, say the corrections to the electron's charge, moment, and everything. These were so easy to be measured. Okay, so then the single photon detection, you know, coming in h nu, so easy to detect. I think so. Gravity, all these are requiring extraordinarily, you know, low energy precision, you know, measuring very small quanta, or measuring going to very high energies, or coming, you know, extremely close. You cannot come as close because of the dimension of the object. So essentially, we are left with this hard thing. Yeah, the hard things have only started like 10 or 20 years ago, even for electromagnetic phenomena, the superposition, entanglement, and we are kind of strangely left with that to, you know. I remember, so Freeman Dyson told that you will never detect any quantum feature just because of this, you know, you cannot detect the quanta of gravitational waves. So somehow we are, the easy thing, the normal easy thing is hard, and the hard thing is the only way.
So I imagined this question had been asked every time you've given a talk. And my question really is, which experiment should I go look at? Because I'd like to understand the electromagnetic experiment. So can you point me to the right
ion trap experiment? Yeah. I mean, you know, we already have kind of ongoing thoughts that whether we should do something about it, and we had discussions and stuff with experiment, but there's no explicitly duplication of our experiment which has been done. But any ion trap entangling experiment is essentially what I spoke about. So look at Christoph Wunderlich's papers. Maybe there's a review on entangling using, you know.
Thank you.
The language may be a bit strange because they do not fundamentally use the Coulomb interaction. They use they convert it to the common vibrational modes, and then they use that language. But it's the same thing.
Thank you.
I have a follow-up question on the same point.
Mm-hmm. Hello. Yeah. Hi. Hi. So I heard your interesting talk last. So I went to see the previous talk. So I understand you gave one. Yeah.
Thank you. Yeah, thank you for this beautiful talk. All this is really exciting for all of us, I guess. Yeah. So I have a question on coherence. It's important here that you have that the objects that you want to entangle have masses that are large enough. The relevant scale is the Planck mass, so we have to get to micrograms. The question is, once you get to objects that have this mass, how much control do we have of the coherence of these objects? because they are necessarily composite. And when I want to check if the two are entangled, I can think of them as two elementary, but then there's the coherence within each one of them. Or if I think of gravitational interaction, I can model them as two elementary objects and look at the interaction of one with the other. But in fact, I should check that each portion of one is entangled with each portion of the other, and then coherence might destroy that kind of correlation. So the question is, how does one control this effect, and how much do we know about it?
Okay, now that's a very good question. So that's essentially one of the key things which I did not get too much time to discuss, though practicalities was in my target. I kind of went fast over them. I should already say that the second part of your question, I haven't had a great deal of thought about the gravity between the parts due to the shape or vibrations. That one I'm not. I haven't had much thought about it, but other things we have had a lot of thought about, and I can tell you. So essentially, just I don't want to depress people, but the world record is 10 to the power 4 atoms. Okay? So this is unfortunately like 10 to the power minus 23 or 22 kgs. Okay, so we are going 10 to the power minus 14 kg is a huge jump from that. Okay, now what do we? So we have calculated, of course, what are the necessities to do these things. So the main requirements for the coherence are there are two main things in the coherence. So so maybe third thing also I'll tell you, but two main things of the coherence for the mass are, one is that it should not emit a black body radiation. So internally, it should not emit black body radiation whose wavelength is shorter than the separation, because then a single emission tells you which place it was, gives which path information, and the coherence is completely destroyed. Okay, it's slightly more technical than that, because there's a time over which the experiment will go, and you will collect many photons by that time. So it's not just lambda, it's lambda by square root of n, how many photons you collect from the short noise. Okay, so essentially this gives us a temperature of the internal one. This turns out to be about a Kelvin. Okay, or kind of 50 millikelvin, something like that. The exact things would be there in either in our paper or in the supplementary material of that. Okay, so it is between hundreds of 50 millikelvin to one Kelvin. I've forgotten that. So you need to have this 100 micron separation for this micrometer radius things. Okay, for the time scale of our experiment is 1 second. And the other thing is that the atoms will collide, scatter off, and reveal the information. So this requires two things at once. A is cooling the atoms, because then their de Broglie wavelength becomes longer, and B, also improving the vacuum so that hardly any atom scatters with that. Okay. Now, interestingly, both are related. The more you cryogenically cool a container, the vacuum becomes better, because things are not dissolved. Things remain absorbed in the surface. Okay, and has been the world records are things which are probably better than what we require. We require 10 to the power minus 15 Pascal. Okay, there's no experimentalists in the audience, but experimentalists say, oh, when we say this thing. But there is the star in this, Jerry Gabrielse, who had these spinning traps with electrons, and electrons going around for hundreds of days. Okay, so they have so good vacuum that they cannot measure. So they say they possibly have vacuums of 10 to the power minus 17 or something. Okay, so the coherence can be maintained, but this is the main problem with this thing, that it requires a very multidisciplinary effort. It requires a lot of people joining hands together, and maybe the time will be ripe as soon as there are some small scale demonstrations of individual superpositions and some going towards vacuum. So this is the so these are the two main coherence things, okay? And you asked a third question about the internal environment. That is, again,
Yes.
it's related to that internal cooling, as I mean, that helps in that as well. There are less phonons and things. But the primary internal environment in our case is that acting on the spins. Because you see, you're told, I said that we finally measure spin correlations. So all the entanglement between the spatial positions of the masses are converted to entanglement between spins. Okay, which has one convenience of control, that you can rotate the basis with a microwave pulse and measure in any directions. But the spins can also decohere, of course, with other impurity spins inside. So like, nuclear spins and stuff. Okay. So the decoherence due to phonons and things can be reduced by this internal cooling. That's why we, in one suggestion, we had this bombarding it with this helium gas, which is kind of sympathetically cooling it. But one could try to use better things such as laser cooling of internal modes. Never been demonstrated, but that only very partly demonstrated, but not to the temperatures that we have. So it requires a very clean sample with hardly any nuclear spins. This is a challenge, but people do that for quantum computation anyway. So what is good in this case, our goal is very similar to the goals of quantum computing. The spin coherent part is exactly the same goal. So it will be developed a lot in various fields.
Thank you.
This Eugenia's question has a sort of experimental side and a conceptual side, and I think this beautiful answer by Sougato, very detailed. I mean, for me, it teaches me a lot, and it teaches me two things. I mean, on the one hand, in the experimental side, it's hard, and on the conceptual side, it's easy in the sense that you see where the conditions are, and it's just an issue of physics. It's not an issue of there's no conceptual issue in considering a grain of sand as a single quantum particle, provided that some physics is suppressed. It's cold enough, essentially. So in quantum gravity, we often struggle with this issue. We're often confused between fundamentality and quantum, like if quantum only applied to elementary degrees of freedom. That's obviously not true. And it seems to me that this is Sougato discussion is making very clear. I mean, a grain of sand, you're working with grains of powder, very small nanoparticles or whatever. It's you can view it as just a single particle with spin, provided that there is no physically there's sufficiently small interactions with the degrees of freedom of the components. You say the phonons are not excited, so it's cold enough so they don't move with respect to one another. But conceptually, it's completely possible to think in these terms. Am I right here, Sougato?
Yeah. I think So this is entirely coming because of quantum computation community. I guess that we start regarding quantum synonymous with isolation.
Yeah, good.
Better you can isolate.
Extremely clarifying for me.
Rather than regarding quantum synonymous with fundamental units. So even composites can behave, depict certain quantum behavior. Yeah.
Right.
It is, of course, it becomes more and more difficult for composites to display quantum behavior because they interact just by the virtue of coming, two things interact with proportionately more environment. So that's why it becomes more challenging. Yeah. So this is essentially
So quantum behavior comes in when you isolate the system, right? It's, in some sense, this is
that is true.
which is the other way of saying that you lose it when you declare.
That's true. It becomes entangled with something else. Yeah.
Right.
So essentially, yeah, you have to prevent it to become entangled with anything but what you want it to be entangled with. Yeah, I mean, whole quantum computation is about trying to entangle with things you want it to entangle, but not entangling with anything that you don't want it to entangle with, which is of course a major challenge. Now, this also brings some other deep questions, perhaps at some level, that if we were to think that fundamentally things are a bit entangled with something else to define their position in space-time or something, then maybe one has to think carefully that whether that is consistent with systems, isolated systems displaying interference behavior. You know, I mean, the isolation should be definable, yet. So if one wanted to use entanglement with something to explain that that's where it's localized, that may be a bit dangerous view to take. Yeah. So I'm being very vague here. I'm very vague here.
But entanglement is not
problem. Yeah.
Let me backstop. So there's I mean, the core of quantum mechanics is superposition. You put it this way, and you said after the quantum information evolution. I mean, it's already in Dirac book. Dirac, right? Quantum mechanics, only in terms of superposition principle, which is perfectly fine. But of course, superposition is a funny way. We never see superposition. Right? We talk about superposition, but we don't see superposition. What we see is interference due to superposition. That is also true. So superposition is so this is actually something which Anupam also criticizes me to say. So the picture in the middle is our made picture. We only see the final thing. It's perfectly fine. That's the way we think. I mean, it's perfectly fine. Yeah. But we never see the two things at the same. We never see the cat line, and we never see the up and down together. What we see is interference. So it's a dynamical effect which we interpret in terms of superposition. So that, in that sense, maybe what I said I take back now, because that's probably secured with, because when you do interfere something, you always bring it back to the same point. So maybe you always disentangle and see it.
I have a naive question. So I understand why isolation is going to be useful for quantum computing. You were saying that this type of technology is being developed in the context of quantum computation. What do larger masses help in?
No. So what I meant is not that external superposition, but the spin. The isolation of the spin, the coherence of the spin degree of freedom.
Right. But
so that's what people use as qubits. Yeah. We don't have any practical use of what I said, and that would be great. We don't have any practical use of what I said, these large ones. Its usage is actually indifferent in quantum sensing. The large mass superpositions could help in sensing things, beyond sensing very weak inertial effects. Beyond what we can do now, but not in quantum computing.
So that's about fundamental science, increasing the mass.
Fundamental, but also practical science. I mean, you detect a pothole or something. You just detect inertial things sensitively. So our gravitational wave paper is a little bit in that spirit.
Through interferometry to detect, to make an accelerometer.
Yeah. Okay. Yeah. So you can, if you have larger the masses, then it's n times the effect minus n times the effect in the phase. So you have a amplification.
Yeah, the phase. Yeah, that's right.
Yeah, it's called the Heisenberg limit. So a known state, beats the shot noise limit. So 1 by root n gets replaced by 1 by n in the sensitivity. So those things would be useful in quantum, in a different form of quantum technology, is the external thing. In fact, this is the way I'm redirecting most of my work now at the moment, to see these effector sensors, because then probably we can tell people, we get people inspired with more than one motivation than just fundamentally a quantum nature of gravity. But in quantum computation, the spins are important, the qubits are important, and not this external superposition.
And one more follow-up question. I mean, you were saying that you're making you're hazarding the guess that maybe we can go from 10 to the minus 22, was it, kilos, to 10 to the minus 14.
Yeah.
Which is an 8 orders of magnitude jump. And there are some reasons to believe that if you go closer to the Planck mass scale, you might see something super interesting.
So you're talking about Penrose kind of effects or CSL type of effects?
Yes, or the discreteness of time. I mean, there are many things you can think of. So
yeah, of course, discreteness of time also, yeah, possible, yeah.
How feasible do you think this is in the future? What's your feeling about this, to go close to the Planck mass?
Yeah, I think, I mean, we are also starting to need this for other kind of sensor things we are proposing, like with one of my friends. So we would, I am exploring that kind of thing. Again, you know, between the theorists writing and experimentalist validation, there's a lot of mileage to go. But you know, so again, all the questions are very related. The coherence time is very, so the split. So first of all, if you have a large mass, you require more of a force to split it, to create the superposition.
Right, yes.
So you require stronger kind of, if we were to use our methodology, and state-dependent forces, okay? So the ancillary system should have different behavior corresponding to different forces. So that is one requirement, but and then there's the more difficult thing about maintaining the coherence. So what will happen is that I've not done the computation, but I guess this cooling, internal cooling needed, and the you know, the kind of vacuum needed will again, you know, go up in requirement.
The larger mass, yes.
Yeah.
But so are you saying that, let me see. So if you're thinking of an experiment where the separation is smaller, and thus the gradient of the magnetic field is not necessarily as large, would that make it possible to go?
Exactly, yeah. So that is exactly a domain we are pursuing now. Yeah, that may be possible, and this is, in fact, this domain suffices for a lot of things we are doing now, sensor applications. So so that I would think is more possible. So you sacrifice a bit the separation. Yeah, if it's a single interferometer experiment, then so that's why we were doing that, because single interferometer experiment. In case of gravity, I guess you still need the separation to be comparable to the, you know, the other separation to do something.
I'm asking because we're thinking of how you might actually do something that is sensitive to the that could measure the Planck time interval with Andrea and Pierre and Carlo. And in fact, we're not seeing that. We see that you need small distance because you need to be very sensitive. So you actually,
this is very interesting. So we are also, we have something in this. So some very similar thoughts there. Okay. I think probably that person is also in the audience, and this he has gone. Yeah, so Marco, we are thinking. So that is a I think it's an achievable kind of regime. Yeah, more. I mean, here you can roughly use acceleration equal to F by m kind of thing. You know, so you if you proportionately reduce your demand of distance, then you're fine in terms of.
I see. So you would be left with figuring out a way to cool the thing down still, so that you don't have.
Yeah, but again, all those things depend on the separation.
Okay. It
the
doesn't
coherence.
do
Yeah.
much
Because
with
the cooling is about which path information.
Mhm. Okay, very interesting. We should.
So we are soon coming up with not a fundamental paper, but a practical paper. We also have a fundamental in mind, but we will probably send you the practical one, when it's done. So I think maybe I see Marco in the audience. Maybe he can make some comment on that. His microphone is, maybe. Marco, do you want to say something?
So I guess yes. So looking at the Planck time might require a completely different regime. So completely different type of experiment. Perhaps, I mean, the implicate, so measuring an effect related to the Planck mass might be slightly different conceptually than something to do with the Planck time. So there might be different, different theories that are tested with probing the Planck time or the Planck mass. But perhaps, yes, so just maybe this comment. So,
so thank you. We have, maybe it would be nice to share with you what we have, and you could see what we have in mind in particular, because I mean, it's
Okay.
the whole setup.
We can discuss that offline. Yeah.
Hi, hello.
Hi.
If I can add something on decoherence, on the importance of decoherence. So I with Chiara Marletto and Angelo Bassi, we did some calculations about decoherence, environmental decoherence, and decoherence due to the CSL model. And so we did it in experiment in a setup proposed by Krishnanda and some other scientists. That is basically two spheres, microspheres put close together and trap initially, cool down, and then you can release them and they fall down together and they get entangled. And so we found out that you have to seek for extreme regimes to suppress the environmental decoherence effect. So you have to look for very high vacuums, 10 to the minus 17 pascals, and very low temperatures. And moreover, you have to cool down the particles initially close to the ground state. So you have to have close to zero mean phonon number. So the mean phonon number of the particles has to be close to zero. And in both cases, considered by Krishnanda also, we found out that the CSL model would effectively remove the entanglement between the spheres.
So always, I agree. They always tend to come before the gravity entangling effect. So CSL and even I think Penrosian decoherence, they tend to always come before. Okay. Regarding the so there is a little bit of difference between, I mean, entangling after releasing from a common source and already trying to, so there might be some difference in the parameter regimes for that. I don't know whether good or bad, but yeah. So it's different in a very non-Gaussian problem and more Gaussian problem.
Yeah, I agree. But I think also in your case and in the case of Chiara and Blatko, the coherence due to the CSL effect is very important, and you can also use that as a test of.
Right.
You can use that also as a test of the CSL effect. If you see entanglement in the end, you can say that the CSL effect is not as a value is much weaker than what is expected to be. So yeah, just a remark on the coherence.
Yeah.
Thank you.
I agree. So these, so not only what you're saying is not only will they spoil it, but they could be a more prominent test of the CSL models. Yeah.
Yes, correct. Thank you.
Yep.
Okay. Seems like there are no further questions, if I see that correctly. I think there was a lot and very exciting discussion, very interactive. So I think we can all thank you, Sougato, for this wonderful talk and leading to this discussion. And we hope to see all of you again at the next QIS session.
Okay. Thank you very much. And I say bye to, I see quite a lot of friends' faces here, and some people I know and respect whom I have not met before. Yeah, so that's also good. Yeah. So thank you very much for your attention. Bye.
Thank you very much.
Bye.
Bye. Thank you.
Bye-bye.
Hi.
Hey, how are you?
Hi, how are you? Well, I'm fine, thank you. You?
Good.
How is it there?
Sorry?
How is the situation there?
In Hong Kong, it's pretty good. I mean, we haven't been in lockdown.
Okay, great.
But we're in lockdown from the rest of the world. There are no flights to anywhere or in.
Okay,
But we're
so
in lockdown in Hong Kong. Yes.
yeah, it's like a okay. Well, we are in laboratory now. We restarted the activities. So.
Oh, I saw that you're in the laboratory. Yes, there is a few more people. I don't know if we are bothering. No. Okay. So what's happening? Yeah. So we've lost a bit the track with this everything that happened. We should get back to it. I was thinking about it these days. What's the story? Have we had any news from ordering the parts or something?
Yeah, because we found that a company that make the parts as we want. We asked formally an offer, and they are giving us the offer. I don't know why. Generally, they are quite fast, 1-2 days, but there are 3 days that we are waiting. But there is the company, there are the products, so it's good.
Good. So it's advancing. Let's so yeah, it's been some time now. We should do a Skype. When do you think we should do a meeting with Fabio?
Yeah, we could do. I don't know when your question is.
Anytime. Well, anytime. Like we usually do it on Thursdays, right? That's when he has time.
I guess yes. I remember. Yeah.
So yeah.
Fab is very casual. It's not fixed days that is free, so we can ask.
Okay, but it's very good to know that it's advancing. I mean, we have to advance also on the experimental side. Theoretical side is getting there. It's almost there.
Yeah. That was very interesting. The presentation. I don't understand. I was asking the same question for the Marblito-Vedral if they are more general or not. I don't understand what he thinks. So
what's the question?
The question is if with this experiment without assuming nothing, what is the minimal assumption? Okay, to say something about gravity, because reading the paper by Marblito-Vedral, it seems that they are more general in some way. I don't know. So but from what Bose said, it's like I don't know. Similar approach, not one more general than another. So I was asking, but so he answered in that way. So I don't know if okay.
Well, I mean, Vlatko and Chiara have a more general way of going at it.
Yeah, exactly. Okay. I don't know.
But it depends how much you care about these things. I mean, different communities care about different things. So I don't know. I mean, you know, it's this discussion that's going on forever and everybody has his own opinion. For me, the power of an experiment is what it could disprove, it's not what it proves.
Yeah, yeah, okay.
I mean, the reason this is interesting is because if it doesn't happen, basically every mainstream theory of quantum gravity is dead, including string theory and loop quantum gravity, because linearized quantum gravity is not true, which is the limit of everything.
Yeah, 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 okay, okay.
So that's why it's interesting for me. Because if you don't find that, then everything is dead. So if you find it precisely what precise feature, you know, list of assumptions this is compatible with, you can play with that forever. I mean, depends how much interested you are in that in particular. And it's what Carlo was saying. It's not so much, I mean, even if they, you know, you ask anyone that is doing quantum gravity, they're going to tell you that this, of course, happens, which we do not know for a fact. But, you know, it doesn't teach you anything in particular about, it doesn't guide you on how to build a theory for quantum gravity, because already most people that are doing quantum gravity are assuming linearized quantum gravity. And this thing just agree with linearized quantum gravity. So it's not guiding you more than that.
Okay.
But what is very striking and why people are interested, and also me, is that why on earth would you have something that involves quantum gravity in this infrared low energy regime? You know, and it's what Carlo was saying, that it's a Planck mass, because then you start thinking, okay, wait a minute. If we think about this, maybe there is a new avenue of phenomenology here, which is not high energy, which is not black holes, which is not early universe cosmology, which is something else.
Yeah, yeah.
I mean, all these things are terribly invisible, all these quantum gravity experiments. I mean, there has never been any quantum gravity experiment done, depending on who you talk to. Maybe there is. Maybe you can say that the microwave background is a result of quantum fluctuations, but there is no consensus. So given the complete absence of experiments, somebody comes and says, wait a minute, even in a lab, however difficult it is, in laboratory conditions, low energy, in the gravitational field of the Earth, I can do something that has to do with quantum properties of gravity. I mean, it's, you know, it's intriguing. It's what comes after that is interesting. It's not so much this experiment. But yeah, let's see. Still have time.
And what Carlo was saying about the coherence that can be done by distinguishability. I don't know if you remember the comment of Carlo, in which I don't know if I understand, but when the mass recombined, they won't be the path. Okay, won't be.
Yeah, I mean, roughly what he's saying is that ideally what you want is that all the entanglement is only in the spin degrees of freedom, right?
Yeah, okay.
Because it's somewhere else in some perturbation of the gravitational field. So if you have a field, the gravitational, like space-time in a superposition afterwards, entangled with the state of the spin, then if you measure the gravitational field, whatever that means, if you interact with it, you're gonna make the spin collapse.
Yeah, yeah. Okay, but when you recombine it, you cancel the information, right?
Well, that's what he was saying, that, I mean, when we do it like naively or how to do it, it's zero, right? But he was saying that somebody, I don't know this paper though, somebody did it carefully. And it's a very small entanglement that is present, that is, you know, it's gonna decohere a bit.
Okay, okay, okay. But this can be due because of perturbation of I don't know, but perturbation on the space-time due to the curvature of the trajectory of the mass. I mean, if the mass is in the right, curving perturbates the space, or no? I don't know. What you?
Yes, I mean, somehow the idea that, you know, when you move things here or this way, there are gravitons flying.
Okay, so there is. Okay, no, but because if I imagine, if I think in this way, I think that so becomes completely entangled. So there is totally decoherent. Because if there is some waves, even if very very tiny, okay, there is. So it's not. It shouldn't be totally destroyed, totally mixed state. Finally, if there is some signal that.
Are you saying it should be or it shouldn't be?
Should be a total mixture. If there is some information that go away,
because I don't know. I mean, I'm always confused about this discussion because you have to also detect this, right? You have to measure this, just the fact that it exists. That
because because I think that just because it exists and the one can in principle measure, okay, you should have a mixture. Even if you don't measure, but if you could impose in principle, you, I don't know.
But this discussion about the wedge path information, which I don't know if there is there a definite answer to this?
I don't know. There is if the signal.
The counter argument is usually that this is not specific to gravity, right?
Yeah, but if you, I don't know.
If you do, let me put it this way: since superpositions exist, there's something wrong with this argument, obviously, because we know what you're saying is that there shouldn't be any superposition.
Yeah, okay, maybe there are the state, but are not orthogonal. I mean, if the perturbation, okay, in the right is not orthogonal to the perturbation from the left.
Yeah, that's what I have in mind. That's why I don't know what you're saying. You should get the maximally mixed state. Yes, but you know, you dampen the off-diagonal terms, but you don't.
Perfect. Thank you.
Yeah, I guess just the fact that we see superpositions is telling us that this is what must be happening.
Yeah. Okay. I wanted to ask if some simulation can have a sense from his point of view, but I didn't, because Fabio said if I do too directly question, if he don't understand, say no, it has no sense, could be negative for the.
So if you want to think of further simulations, this would be nice to think about this. I mean, we should put a bit more, finalize this draft so that there is only the experiment maybe going on.
Yeah, sure.
Then open another theoretical thing.
Sure.
But yeah, we should discuss again about doing a fundamental, exploring some fundamental aspect.
Yeah.
These are interesting stuff. Okay, let's.
Thank you very much for the lesson.
Let's catch up soon. So when Fabio wants to do a Skype, let me know, because last time I canceled it. But
yeah. I will. If you are available, I will ask. I will
I'm
ask
available next week. Yes, next couple of weeks I'm around. Next week I'm all the week available.
Perfect. I will ask to Fabio then. Okay.
Good. Happy to see you, and see you soon.
It was a pleasure. See you.
Bye.